So what we're moving into, of course, remember where we're at, the power supply. What do we have? What do we have to make up a power supply? Normally we don't have to have, but what we're working on is we'll come up here and we start off with a power source, right? Okay. And then we come off and then we have a transformer, right? And then we come off this and then we have what? Not yet. Rectifier. Then we come over here, then we have some type of filter. We only covered capacitor filters, but there's several of them, and they're covered really good in the textbook. And then we're going to have a what next? Regulator. And then we have what we call a regulated output. Now, how much of this you have depends on what type of power you need and how good does the DC is at. We have some regulators that we refer to as three-terminal regulators. So think what a regulator has to do. It's got so what we got to do is we got to bring an unregulated in, right? Over here on the output, we're going to have regulated, and what does regulated mean? Even with varying conditions, even with varying loads. Now, regulators for DC power supplies have to not only regulate for changing output loads, it's got to regulate for different input voltages, right? You understand? It's always a tolerance. I mean, it would be like the air pressure in your tire. Is there a tolerance there? I mean, can you go out there and put 100 pounds in there? No. Can you put 0 pounds in there? No. You got to put a certain pound. So when we say it regulates, it's going to regulate over a set number of loads, right? You understand? And also a set number of input conditions. So I can't regulate if my power supply is unplugged, I'm not going to get regulated voltage, right? You understand? Or if I set it up to be able to regulate on the input voltage of around 90 volts and it drops down to 80 volts, it's not going to regulate. So everything's got a range that it guarantees it can regulate at. It's just like your car. So that regulator that's regulating the output of your alternator has a set range that it can handle. If you get it out of that range, then by George, it can't handle it anymore. Like most regulators don't even start working until you're right around 1,000 RPM. So if you ever rode a Harley and you toned that thing down, you had to rev the motor up, or you wouldn't be charging your battery, right? You understand? And then, of course, we have to have a common. Now, we're going to find out that we got a lot of things that has 3 terminals, and we call these 3-terminal regulators. That's all they are. So they got one of the inputs is where you're going to put your unregulated. One of your pins is going to be your regulated, and one of your pins are going to be your common. And we call these things 3-terminal regulators. If they're called 3-terminal regulators, I mean, you could have more complicated regulators than these. These are pretty straightforward. Well, I'll deliver it to y'all different ones. Well, it's always going to step it down because you can't regulate more than you got. Okay. So over here, what we got is we've got this garbage right here, right? That's not a good thing. It's got this garbage right here, unregulated. And if the load goes up, then the ripple gets bigger. If it goes down, the ripple gets okay. So let's say, but my regulator might be 5 volts. So over here, I'm going to be putting this garbage in here, but it's got to be greater than 5 volts. And over here, this would regulate at 5 volts. So we got to give it enough leeway so when the load changes, that bottom pulse does not get into my regulated voltage. And that's the way regulators work. So we can never get out more than we put in, we got to put more in than we're going to get out. And then what we do is we regulate below the unregulated portion of our input load. Understand? Yeah, so over here when we charge and discharge that capacitor, how far it discharges is dependent on the load, right? You understand? We call it voltage ripple peak to peak. And what is it? It's I over what? FC. So if I goes up, then ripple voltage goes up. If I goes down, ripple. And this is the load. This is what you're loading out here. So this is the output of the power supply right there. Understand? So if we can calculate this for the load, and so when you come up, you got to come up with a load. You can't just say I'm gonna. So your power supply is going to be able to deliver a certain current. And if you ever look at a power supply, somewhere on there is the current that it's able to deliver. If you make it deliver more than that, then it's going to go out of regulation, and it's not going to give you that 15 volts or that 12 volts or that 24 volts anymore. So if I look at the regulator on this power supply. So this power supply can give me 20 volts at 3.325 amps. And that's what it, so if I try to get more current out of it, it's not going to regulate. If I try to get less, it'll work fine, right? You understand that? Maybe. So these are 3-terminal regulators, and this would be a basic setup. 3-terminal regulators, they come in all sizes. These are 3-terminal regulators. I did hook my camera up, and I think I got this other one hooked up. So this is called a TO3 case. This is the 5-volt regulator that's in our trainers. And it's 3-terminal because this whole case is one of your terminals. Notice it's all metal. So these TO3s, one of your terminals is actually the case. And then, what's that? For TO3s, it's always common. By the way, this is JEDEC registered Joint Electronic Device Council. So this package is a registered open technology. So that means all your people that make voltage regulators, high current voltage regulators, are probably going to use what? This pack. You're looking at what we call a TO220 pack. That's a TO220 pack. And what they do is when they come up with these packages, is normally they register with JEDEC, and then if they're registered with JEDEC, they're open technology. So that means all your drafting programs and all the programs that decide how to do that now can have a mask to put in there to make these printed circuit boards. They don't have to make them. So this is an open technology package. So this could be a lot of things. It could be an SCR, it could be a CMOS, it could be a FET, it could be a MOSFET, it could be a transistor, a BJT, or it could be a regulator. Because all a regulator requires is 3 pins. It requires an unregulated in, a regulated out, and a common. So just because you see one of these guys don't mean this is actually an integrated circuit. There's a lot to it. We can look at the insides right now. It won't make much sense, but there's a lot to this thing. But what you usually have to do, so when we set this thing up, you need to look at the data sheet. They'll give you all this information on what you need to do. Okay. But they come different sizes. I didn't give out these. So this is, now, what current they can handle would depend on the physical size, right? You understand? But physical size costs money. So this is the 3-terminal regulator right here. This is a TO92 case. But all it needs is 3 terminals. This guy here would be rated in milliamps, right? You understand? This guy right here is, I think our power supplies are 3 amp supplies. So when we look at this picture right here, I mean, they come in all different sizes, you know, sizes and shapes to do what they need to do. Now we have 2 predominant series. We have what we call the 7800 series. And what they'll do is they'll start off with 78, and this right here will be the voltage that they regulate at. So a 7808 would be an 8-volt regulator. 7812 would be a what? It would be a 12-volt regulator. The 79, these are positive regulators. So these give us a positive voltage. The 7900 series follows the same exact technique, but these are negative regulators. So a 7905 would be a negative 5 volt regulator. A 7908 would be a negative 8 volt regulator. Are we okay? And it's really straightforward. So this would be the setup using a full wave bridge. So we start off with a watt, power source. Then normally we have a watt transformer. Then we have a rectifier. Then we have our filter. Now normally on your regulators you have to put a post filter, and they'll give you the size because the regulator's trying to move that output around, and that filters out that and makes it regulate better. So normally we have a post regulator or a after regulator, right? You understand that? I'm sorry, filter, but notice it's really small compared to this. So over here this is 1,000 microfarad. Over here this is, and these guys are going to be rated at a voltage, and they're going to be rated at a current. So they're really easy to use. So you
once it's regulated, do you have that much current?
No, you don't, but you got the regulator trying to regulate. So we have a filter out there that basically prevents garbage from getting back into the regulator. What it is. Yeah. So a pretty straightforward circuit. And these guys are really, but they're fixed regulators. The problem, so this guy here would be, this is what we use. So when we look at the trainer, and we've got that 5 volt supply up there, it's going to be a 78. It's going to be a 7805. The negative 5 volts is going to be a 7905. I don't think it has a negative 5, but it has a plus and minus 12. So the plus is going to be a 7812. The negative is going to be a 7912. But then we've got two variable regulators, right? You understand? So the most predominant variable regulator is a 317, and I can't remember what the negative regulator is. We'll have to look at it. And this guy's real easy to use too. I mean, it's real easy to set up. We bring in our unregulated right here. We have to make sure we have enough so we stay out of the ripple for the maximum voltage you'd get out of the thing. And then this is the way you set it up. By the way, what it does is this guy right here maintains 1.2 volts between the output and that right there. So what happens if you adjust this down, then this has got to go up higher to maintain that 1.2 volts, and that's the way that thing regulates. This is a really nice regulator. This is what's on my power supply that I built at home.
Why is the input smaller?
This is not this is a filter capacitor for the regulator. This is not a filter capacitor for your big guy over here. This is just what they recommend. So this one they recommend, and if you look at the data sheets, they talk about the distance from your rectifier. Depends on what you have to do and what you have to do there. But this is all in the data sheets that tell you. So this guy needs an input capacitor, filtered capacitor, and it needs an output filtering capacitor to regulate real well. But this is just a rheostat, and it's got all the calculations. If y'all are interested, I could give those to you to calculate the size of this resistor depending on what size pot you use down there. Or rheostat. Normally, we don't see many rheostats anymore. And why is that? Well, we got a pot that can serve two functions. If I come over and do this, and then I come over here and this would be 1, 2, and 3. We're using it as a pot. If we come over here and take the wiper and connect it to one of the ends, this makes a pot act like a rheostat. So that's what I'm saying. So we don't see hardly any rheostats anymore, because now I've got a device that they can sell that serves two functions. We can wire it to act like a rheostat, or we can use it as a pot. And all we do to make it act like a rheostat is just take the wiper, pin 2, and connect it to one side. That's all you have to do. Oh, 1.25 volts. So the minimum on this one, you could drop it down, would be 1.25 volts. And that's if you set that right there to maximum. So this guy here is really neat. Really neat. like I said, if I can remember. So you can look at the one you got. So somewhere on there it's going to be a 78 or 79 something. It might have some letters in front of it because that's usually the manufacturer code. And then you're going to either have a 78 something or a 79 something, whichever one you got. You can't check these things with a voltmeter or ohm meter. Even though they got a lot of PN junctions in there, they got so many you can check them. So about the only way you can check these is to power them up. Are we okay? 3-terminal regulators all over the place. And we're going to see these in the trainer. We got all 3 of these in the trainer. We got a 7805. Well, that's not true. We're using the ones in the trainer was originally 74 H05s. And what the H05 was that these were high current versions of these. We couldn't find these. So what we did is we just looked for another 3-terminal 5-volt regulator that was rated at, I think, 5 amps. So what we're doing, and I don't know if I have the data sheet out there or not, we're using the LM323, and this is a 5-volt regulator. So just because, you know, so the 7800 and 7900 series are okay, but there's other people that puts out these things under different numbers. So these are the ones that we use in the trainer. And this is a LM3 317, so this is that 3-terminal regulator right here. And we've got these in the TO220 package. So the size determines how much current they can handle, right? You understand that? So yeah, we bought the 78H05 is a very unforgiving IC. And you get people in DC and stuff like that, and they short out the 5-volt supply and it usually pops it. So we got quite a few of these back there. And they're real easy to replace. You know, we'll show you all those in the trainer and show you how easy it is to replace them and troubleshoot those. And of course, the most used circuit in electronics is the power supply. And since it's the most used circuit, it's the one that goes bad first, right? You understand? Or goes bad a lot. I'm not going to say bad first. Well, depends on how people, we bought some of these in the trainer right off the bat. First time they used them in DC. Don't know the difference between an amp meter and a voltmeter, and they didn't know they'd short them out. So that's one of the reasons we go by and check all these circuits to see if they're okay. What we're going to do now is talk about the actual regulator itself. So somewhere inside this thing is a special diode that we call a Zener diode. This is in your textbook on page 122. Zener diodes. So we pick up so we know we have rectifier diodes, which are designed, these are low frequency diodes. They're designed to take AC, usually 50 to 60 hertz, and convert it over to DC. Then we have what we call small signal diodes. These guys are designed to operate at real high frequencies, but they can't handle a lot of current. And then we got these guys. These guys are what we call Zener diodes. And they have this is the VI characteristic curve that we just looked at, right? You understand? So we come over here right around 7/10 of a volt for silicon and 3/10 of a volt for germanium. The diode starts conducting, and then it's not straight; it's a slant, right? You understand that? Because now we're dealing with the resistance of the semiconductor. When we start reverse biasing it, then sooner or later it's going to break over. On regular diodes, this right here is bad.
So that's correct, but look at this
This takes a lot more energy to get current, a lot less energy to get the current to start flowing. This takes a little bit of energy. But you can see as soon as I put a voltage on there, we had what? We had about 8 volts. And already we had microamps. I'm sorry, we had nanoamps of current. So as soon as you put voltage across anything, you're going to have current flow through it. If you've got a path, right? You understand. So right now, if we're causing electrons to move. And then it did what? Then it was pretty well, ours had a little slope, so this is not exactly right. So ours had a little slope to it, right? Because as we increased the voltage, and then what did it do? Then it just avalanched. We didn't get to avalanche it real good. We avalanched one real good. But why didn't we hurt it? Well, we had that 1 mega ohm resistor in there protecting that diode, right? You understand? So our current never got up above. What was the last voltage we had? I don't remember. About 14 volts when it finally broke over. So the current flow was still well below what would cause damage to diode. But notice over here, this voltage stays relatively constant even though the current flow through the Zener, through the diode, changes. No, it's changing. As soon as we get past this, which we call the knee, by the way, then the voltage across the diode stays relatively constant. The problem is a regular diode would burn up. A Zener diode won't unless you get too far down here. Now, eventually, something's going to happen down here, right? You understand that? Because we're forcing current through the reverse direction. So the Zener diode has a special symbol. This is a Zener diode. So a rectifier diode or a small signal diode looks like this, right? Now notice on this one we have these little tips over here. If you see that symbol, it means it's a Zener diode. Everybody okay? A Zener diode is designed to operate in the reverse breakover region, as long as you don't put too much current flow through it. Y'all understand that? A silicon p-n junction, a Zener diode, is specifically designed to work and operate in the reverse breakdown region, reverse biased. And that's what it says right off here. If I look at start reading about the Zener diode, you'll see that this guy here is designed to operate in the reverse breakdown region. But we're going to have to protect it with a resistor. So we'll never run these things without a resistor. But the resistor don't have to be 10 meg. The resistor can be ohms. These guys are designed to handle a little bit of current. They're designed to dissipate some power. This is what we just got shown, right? Now, there's no such thing as a perfect regulator, but you see, we still have this slant, right? You understand. So the output of the Zener will go up as the current goes up and down if the current goes down. If you can maintain a pretty constant current flow through it, then it'll regulate real well. Are we okay so far? Yes or no? So as the reverse voltage increases, the reverse current remains fairly small until it reaches what we call the knee. You'll understand why it's called the knee, because it looks like a wall. It looks like a knee. Breakdown effects begins at the knee. At this point, the current increases rapidly. The breakdown voltage remains essentially constant. It doesn't stay constant, but it's essentially constant. The Zener diode keeps almost a constant voltage across the terminals within a certain range of currents. So we got two currents. We got one we're going to call IZK. What do you think that means? Zener current at the knee. And then you got one called IZ max. I just told y'all what it is. This is the maximum current. As long as if we get above IC max, the Zener could burn up. If we get it below the knee, then the Zener's not going to regulate it. Y'all understand that so far? Everybody okay? So we've got IZK, we got IZT. IZT is, when I look at a Zener and it says it's got a, so we're going to call this VZ, this is the Zener voltage. If it says it's 5.1 volts, that's going to be at a certain current that we call the Zener test current. If we operate it above IZT, the output is going to be a little higher. If I operate it below IZT, the output is going to be a little lower. That makes sense? Yeah, okay. This is IZK. So IZK as soon as we clear the knee. So it's not actually the knee current, it's as soon as it clears the knee. So y'all understand these three currents. So what I want to do, I want to operate it somewhere between what? IZK and IZ maximum. If I operate it between those, the Zener's going to regulate. It's not going to be perfect regulation. Like I said, there's no such thing as perfect regulation. It's just like you go out on your car and you put your voltmeter across your battery with your car running. It's going to measure about 14.3 volts. You go in there and turn on your air conditioner and everything, the voltage is going to drop a little bit. Not much, but it's still going to drop. You turn the lights off and everything, it's going to come up because it's going to regulate within a range. Are we okay? Yes or no? So we operate a Zener. A Zener is not normally operated in a circuit reverse biased. But when you check it with an ohm, if you operate it forward biased, it's going to act just like a silicon diode. Zeners are silicon, by the way. So around 0.7 of a volt, they're going to start conducting. If you operate it below the breakover voltage, it'll look just like a diode. Just like a diode. It'll block on one way and pass on the other. It's when you operate it above that knee current, above that Zener voltage, when this thing here actually comes into play. Everybody understand this? So if I'm going to check this with my own meter on the diode scale, it'd check just like a diode. Your meter is not going to break that thing over. IZK, to regulate a Zener, the Zener must always be operated above or more than this current. IZT, the current flow where VZ is established, the circuit should be designed to regulate as close to this as we possibly can. Right? Does that make sense? IZM operates above this current will damage the Zener. This current is not given in the data sheets, but what they do give you is they give you the maximum power. And so what we do to calculate this is we look at the max. I is equal to P over V. That's a very important formula to know. So what I do here, so IZ max is going to be equal to the power given for the Zener divided by the Zener voltage. And that'll give us IZ max. So I've never seen a data sheet where they give you IZM. Because you can calculate it very easy, right? Everybody with me so far? Any questions so far? Yes or no? So basically the Zener is equivalent to a voltage source. But it don't create a voltage. We have to have a true voltage source. So if I've got a 12-volt battery, when we do all our calculations, we put everything in parallel with that battery, right? You understand? Put our circuits in parallel with that battery. Even if it's a series circuit, the whole circuit itself is in parallel with the battery. Well, that's what we're going to do with the Zener. So what we're going to do with the Zener is we're going to start off, we're going to have a resistor, which we're going to refer to RS. And then we're going to come over here and we're going to put our Zener for a positive power supply. And then we're going to come over here and then we're going to put our loads right here. So if this is a 5.1 volt Zener, then what would the voltage be across my load? Yeah, it's going to be 5.1 volts because it's in parallel. So we consider this to be basically the source of our voltage, even though over here, what we're going to do is we're going to have unregulated. Over here we'll have what we call regulated. And this is going to be positive unregulated. We put the Zener in there, reverse bias. If we don't put it in there, reverse bias, it won't regulate. And we're not going to calculate Zener impedance, by the way, so we're okay. So this is what we're looking at, guys. I mean, this is basically what we got. So that Zener, once it's in a circuit, it's going to act like a little battery like that. Now, it's not producing the voltage, it's regulating the voltage that's there, right? You understand? But to my loads, it looks like the source. By the way, this would be first approximation, and we know it's not that. We know it's got a slant to it, right? Everybody follow me so far? We okay? So this is what actually happens in real life right here. So the output is going to do what? It's going to change, but it's not going to change that much. So every power supply you'll see, if you load it, the output's going to drop down a little bit, and if you unload it, it's going to go up a little bit. Not much, but it's going to do that. Are we okay? ZZ is what they use to calculate the impedance of the Zener or the resistance of the Zener. So what we would do is we would measure this current, the change in current. So anytime you see the term delta, this is what we call the change in. Okay. So what we're saying right here, if this was 100 milliamps, and then this right here was 200 milliamps, and my Zener voltage changed from 5 volts to 4.5 volts, then that's the way we would calculate the impedance. So what I would do up here, I would say, okay, it changed 0.5 volts, and it changed 100 milliamps, and that would give us, that's R is equal to V over I, and that would give me the impedance of the meter. But we really don't need to do that, because guess what? In your data sheet, they're going to give you this. They're going to give you this, but that's the way they calculate. So we're not going to calculate it because it's going to be given in the data sheets. Understand, Larry? So what did it come up being? Here they said, okay, for 50 millivolts, 5 milliamps. So what would be the impedance? I should have gave y'all the answer. So here the Zener voltage changed 50 millivolts. Here the Zener current changed 5 milliamps. So that would be the way they would. That's just the way they calculate it. What? So what would it come up, guys? Huh? 10 ohms. And of course, if you knew this, then you could calculate the voltage over any way. So now, if I knew the current, I can multiply it by this, and that would give me what my voltage would change. So these are some of the things we're going to look at. Let's go ahead and look at our data sheet. Hopefully y'all got Blackboard opened up. We're going to be dealing with the 4700 series of Zener diodes. Now, there's a lot of people make Zener diodes. The 4700 series is a very common one. There's several manufacturers that make the 4700 series of Zener diodes. Are we okay? So these are made by, we're going to open up that data. These are the series of 4700 Zener diodes made by Motorola. Y'all heard of Motorola, right? They've come out with a new phone, call it Motorola. My grandson said that. Said, how'd they come up with that stupid name? I said, it's Motorola. Motorola led the cell phone market for a long time, but they were kind of like IBM in the personal computer, is that they didn't follow technology. They said, we're the big guys, everybody's going to do what we do, and everybody said, well. So Motorola basically lost out a lot. Huh?
They were the one that had big white dog.
No, that was RCA.
RCA.
So this is our diode. So right off the bat, all these are watt. These are all 1 watt Zeners. So that now I can calculate IZ max. So the 4700 series of Zeners are 1 watt Zeners. Y'all understand that? So we get down here, it gives us the die rating factor. So it says these guys are set up, so power supply, ambient dissipates, ambient temperature, 50 degrees centigrade, and then it says for every degree above 50 degrees centigrade, then I have to die rate that by a 6 point, can y'all read that on y'all's? 6.6 millivolts per degree centigrade. Y'all understand that? Yes or no? Huh? So what we're saying is, let's see if I got a blank sheet somewhere. I know I got one somewhere. This right here would be good enough. So I can come over here, let's say, so it's rated at 1 watt. But it's guaranteed to be 1 watt or better up to 50 degrees centigrade. Which is hot, guys. Okay. So let's say I'm going to operate it at 80 degrees. Well, what I'm going to do is the difference is 30 degrees. I would come up there and multiply that by 6.67 milli. Y'all understand that? What I come up and get. So, huh? 20 watt. I can't take. Huh? So 30 times 6.67 milli. So that's milli, right? You understand? 200 watt? 200 milli? Is that close enough? So that means my Zener would only handle 800 milliwatts. Y'all understand that? Yes or no? Huh? Now this is what Joey came up. I don't have my calculator up here. Yes, I do. So that's what they mean by diode. As long as I was below 50, we would use 1 watt. Actually, it would get better the further down. If I got above 50, then you would have to die rate it. You'd have to die rate the maximum by 2.5 milliwatts per degree. Above 50, right? You understand? So 50, this is 80. What would be, how much above 50 is? It's 30 degrees. I'd multiply that by the die rating, come up with that, and I would subtract that from the rate, from the actual rate. So somewhere over there we got the Zener test current. So let's look at this again. Let me first right here. Okay. So that's 1 watt. By the way, that varies with temperature, length. It varies with a lot of things. So the longer the leads, the more time it takes for the temperature to dissipate from the Zener down into the circuit card. So the shorter you can make those leads, the better it is. Okay, so here's all the Zeners. So let's say I'm looking at a 1N4744. Y'all see that? It's right here. Are we okay? The Zener voltage is what? 15 volts. It's a Zener. 15 volts at IZT. Y'all understand? Are y'all staying with me so far? We're doing the 1N4744. 1N4744. Okay. We follow that over. It's a watt. 15 volt Zener. Right? What's the test current? 1.5 milliamp or 1.7 milliamp. Okay, y'all see that? So that 15 volts is only guaranteed at 1.7 milliamps. If you operate it above 1.7 milliamps reverse current, it's going to drop a little more. Below that, it's going to drop a little less. What's that? Oh, it says 17, I'm sorry. Yeah, 17 milliamps. You know what I was looking at? Y'all see what I'm looking at? I was looking at my pointer. See the dot on my pointer?
Oh.
See my little dot? So I had my dot setter, guys. See that? Okay. Zener test, and there's your Zener resistance. So this guy here is going to have about what? About 5 ohms worth of resistance. That's me. I'm on the wrong one.
14.
Yeah, about 14 ohms. Okay. Then we got IZK. What's IZK? You okay? 250 microamps, right? Okay. Leakage current, this guy's going to be anywhere between about 5 microamps at 11.4 volts, and then surge current. So this guy here could handle up to a lot of milliamps for a short amount of time, right? So the important things we're looking at is the Zener voltage, right? And the other thing we need to know is the knee current. Are we okay? The other stuff we really don't need. By the way, let's go down here and look at note 1. So just about everything in electronics has a tolerance. Okay, so it says tolerance of types, number designators. The normal Zener tolerance is plus or minus 10%. A standard tolerance of plus or minus 5% on individual units is also available and is indicated by the suffixing of a what? A. So that means a 1N4744A would have a what? Would have a 5% tolerance. A 1N4744 would have a 10% tolerance. Y'all understand that? So that's like the color bands on your resistors. Normally when we use these things or design these circuits, they're not real hard. They're not real hard. Is that the two things we're interested in is the Zener voltage and the knee current. Because we're always going to have, well, that's not true. We're concerned with the knee current because we always have to operate it above the knee, right? You understand? Yes or no? And we have to operate it below IZ max. So it means on this guy, to make it regulate, I've got to have at least 250 microamps of current flow through that. Any questions? Yes or no? By the way, we should have had this lecture Monday. What happened with Monday? We did the meter. No, what did I say about the test? Huh? For what test? I thought I did. It's on there. Y'all can't do it yet anyway. We hadn't entered the emails yet. I'll send it out when it's available. The link, if it's not there, somewhere on there, it should be a link. I think I put it. Well, the link wasn't there until after we did it Monday. So if you looked at it before Monday, the link was not there. So you're anxious to do that? I believe y'all could do okay. Most y'all could do okay, especially with the PowerPoints. And like I said, there's no time, but I don't think you can quit it and come back. I think, I'm not sure. Like I said, it's not our test. So let's look at a 5.1 volt Zener. Y'all find what number would we use? $47, 1N37, 4733, right? Everybody okay? Yes or no? Okay. Everybody okay? Okay. What would the IZ max be? Let's calculate that. So IZ max would be equal to would be equal to 1 watt. These are all 1 watt Zeners divided by 5.1. That's the Zener voltage, right? So what would be our maximum current? Everybody okay? Yes or no? Everybody got that? Everybody got that? Larry got that. So that means as long as I operate it above 250 microamps, and then I operate it below 196 milliamps, this guy will regulate. Now what we would like to do is we would actually operate it as IZT, Zener test current, or around that. It's going to be hard to do. Are we okay? Yes or no? Questions? If I operated above 196 milliamps, that means we could burn it up. If I operated below 250 microamps, it will go out of regulation. I had a better copy of than y'all had. But we're dealing with the 33, right? 5.1 volt. So Zener diodes can be used as voltage regulators in low current applications. But what we're going to find out before long is we have a device called a transistor, a bipolar transistor, that gives us current gain. So what we'll find out is that we can create a regulated power supply by using the Zener as the voltage reference, and then feed that into a bipolar transistor and get what current we need out of our power supply. It takes a varying DC, which is unregulated, and keeps its output relatively constant, right? You understand? The Zener can work over a set range of currents. If we operate it below IZK, it's going to go out of regulation. If we operate it above IZ max, it's going to burn up. But as long as we operate it between those things, it's going to regulate pretty good. It's going to be a regular diode, but it's not going to regulate. Yeah, below IZK, it acts like a diode. Above IZK, it acts like a Zener. A regular diode above breakdown acts like a Zener, but you're going to burn it up. Because almost always a rectifier diode has no protection. The rectifier diodes are connected directly to the transformer. How much resistance does a transformer have? Almost none. So those diodes are not protected at all. So if we let those things, if we use the wrong size transformer and it exceeds the breakover voltage, you saw what could happen in there. Made some of y'all jump, didn't it? I even jumped. So we're going to require a series limiting resistor, current limiting resistor. If we don't have that resistor in there and we reverse bias this thing, it's gonna pop on us, right? Y'all understand that? So anytime we use this Zener, we're always going to have a resistor to protect. Oh, Zeners are used all over the place. In fact, if we look at a 7805, somewhere is a Zener in there setting the voltage reference. So just about all voltage regulators that I know of use a Zener to reference their voltage. But we can also make them ourselves. What's nice is I might have a 12 volt supply, but I need a 5 volt supply, and I want it to be regulated. Well, I can take the output of 12 volt supply and run it into a Zener. So I got 12 volts right here, and on this side, I would have 5 volts. So we do this a lot, especially in where we need multiple DC levels. Does that make sense? So you'll see Zeners all over the place. We use them for clamping circuits. So, you know, I'm coming into my PLC. And by George, and it comes through a little photodiode, which we'll talk about later on. Man, I want to protect that photodiode, and some idiot comes up here and hooks this up to 50 volts. Well, that would bop the input on my PLC. But what we would do is we'd come over here and we'd put a little Zener right there that's rated at whatever that thing needs. This little diode might work at 5.1 volts. Over here, I might be putting 24 volts on there. But we automatically do that, right? So understand. So we use them to clamp voltages to make sure voltages don't get above what they're supposed to be. We have all types of applications. We can use them for snubber circuits where they're deliberately supposed to short out. Well, we'll put them back to back and put it on an AC circuit. So if the AC gets too big, it'll clamp it off. So we use these things all over the place. PLCs, though, if you ever look at a DC module on a PLC, if you looked at the circuit, it's going to be a resistor in there. And then what's it going to be? It's going to be a Zener, and then it's going to be a photodiode right here. And that's the way it works. And that would be the actual input port on the PLC itself. And then we use what we call an optical coupler or opto isolator. Any voltage applied to the Zener that is above the knee voltage will be basically a short circuit. So this is why we got to protect that with a resistor, right? A resistor that is connected in series with the Zener, called RS, is required to drop the difference between the unregulated voltage and the regulated voltage. So sizing this resistor, folks, is very critical. Calculating size of this resistor is critical to the operation of the circuit. If I choose a resistor that's too small, we'll burn our Zener up. If I choose a resistor that's too large, we'll go out of regulation. And it's not hard to size. Guess what law we're going to use? Well, we're going to use Ohm's law. R is equal to what? V over I. All we got to do is figure out what V and what I. So this is a typical regulator. So over here, this is all that garbage we got over here. So this would be our power supply. Then we would have our transformers. Then we would have our rectifiers, then we would have our filter, and then that would be right here. So this over here is doing this stuff right here. Then we have our Zener, and over here, this is where we're going to connect our load. Right now, we'll use a resistor as a load. Resistors make real good loads. And this would be a positive regulator because we have to reverse bias this thing. So we're going to put the positive toward the cathode, and we're going to put the common or the negative toward the anode. Everybody understand that? If I wanted a negative power supply, I would put a negative up here, and I would just put I'd change my Zener around. Now what's happening is this guy over here is varying. So let's just make up something. Let's say it's varying from 8 up to 10 volts. That would be this right here. So this would be the trough, and that would be the peak. So that's varying. And this, we would make sure this is maximum. So whatever we want to regulate at, we would always, that would be where the 8 volts was at. So if I was setting up a plus, would give a little leeway. So if I was trying to develop a 100 milliamp supply, then I would calculate the ripple voltage of the 100 millivolts. Are we okay so far? Okay. So I can never put DC across a speaker in a car. If you put DC across a speaker in a car, you would burn your speaker up. Your speaker requires AC. Okay, but my battery is nothing but what? Positive, but it's positive DC. Well, how in the world am I going to get AC if I don't have negative DC? You understand? So if I'm going to generate AC from DC, this right here would have to be positive DC, but this right here is going to have to be what? Negative. So if I didn't have the ability to generate negative DC, then we wouldn't have radios. Because we'd have to come up with another method to have speakers. Speakers, you don't put DC across speakers, because if you put DC across speakers, they act like a piece of wire. Have you ever opened up a speaker? All it is just a bunch of wire. Well, see, what we have is when we put AC on a coil of wire, we end up with another formula we call X of L is equal to 2 pi FL, and this is another type of opposition, but now we get opposition from frequency. If I put DC on that coil, frequency would be 0. I have no additional opposition except for the resistance of the wire. Your speaker would burn up just like that. Either your output of your amplifier is going to burn up, or your speaker is going to burn up. So how are they going to generate AC when my battery doesn't have negative? Well, they come in and they run it through an oscillator circuit. They generate AC. They re-rectify it and generate a negative and positive DC. So inside my radio, I have a negative and positive DC. The positive is used to generate the positive side of the cycle, and the negative is used to generate the negative side. If I want to change the direction of a DC motor, we can change the polarities on the DC motor. So one way we do it is we have a positive DC to make it run in one direction, and then we switch it to a negative DC to make it go to another. Now there's other ways we do it, but it's a lot more complicated to reverse. So anytime so this guy right here, this is called a function generator. Okay, and to control it, the advantage of DC over AC is we can electronically control it. But I can go out and buy a thing called an inverter for my car. What does that inverter do for you? Takes a 12-volt positive battery and converts it into AC. Well, how can it get AC? Well, by George, it's going to have to somehow generate a positive and a negative supply. So we use negative supplies all over the place. Now, positive supplies are the most predominant power supply. Right? You understand that? But we still have negatives too. I mean, every radio you got. So I got a cell phone right here that I put earphones in. This guy right's got to generate AC. So I mean, somehow it's got to generate a positive DC and a negative DC. These speakers right here, they've got to do that. These screens right here operate off AC. So to make them turn on and turn off, you put a little AC current on there. But they got a DC power supply, so we got to generate. We got to have what? A negative and positive supply. So that makes sense. So if I'm going to generate AC from DC, I got to have what? I got to have a negative DC and I got to have a positive DC. So that means we got to have negative regulators and we got to have positive regulators. So yeah, what they do in your car radio is they'll run it through a circuit called an oscillator. You know what an oscillator is? That's a guy that's an electronic circuit that turns DC and AC into DC. DC and AC. Now we got AC over here, so what can I do? Well, I can come over here and I can set up a negative, I can set up a positive regulator, and I can set up a negative circuit, right? Y'all understand that? Now we got negative and positive DC. And now I can do what? Now I can run it through an electronic circuit that generate variable speed AC drives. They got to have negative and positive AC that they have the ability to vary. So Alabama Power generates 60 cycles. What if I need 120? What if I need 1,000 cycles? Well, I can't run it off Alabama Power. So what do? Well, we rectify it, turn it into DC, and now that I've got DC, I can electronically control it. I can generate a negative and a positive DC, and then it's up to me what frequency I want. So that's these function generators. That's what you're doing. You get AC out of these, but you get the ability to vary the what, Barry? You get the ability to vary the amplitude, and you get the ability to vary the frequency, but it's done electronically. So, did that answer your question? I hope so. Okay, guys, let's take a break. We need to get through this. What time does this class get over? 5:30. Because legally, I'm not supposed to give y'all breaks. I'm not supposed to give y'all breaks. The breaks have been moved to the end of the class. This class is supposed to meet 7 hours a week. We meet at 6 hours a week. Because the breaks have been moved to the end of the class. And that still, you need to talk to Nancy about that too. So this is a package that we've got called Electronic Workbench. And what Electronic Workbench does, it allows us to simulate programs. And it does a pretty good job too, but what we can do is we can simulate it with a schematic. So what I've got is I've got a Zener regulated power supply right here. This is going to substitute for my unregulated. Right now I have 12 volts, but we can make this any voltage we want to. Here's my RS. This is my series drop-in resistor. This is showing me my load current. So right now I'm using a rheostat, a pot wired as a rheostat for my load current. And this is showing me my load voltage. We're using a 1N4739A, so this is a 5% tolerance. So look up that Zener and see what it's supposed to be.
5% tolerance.
Oh, we don't need to talk. All we need to do is just look up a 1N4739 and give me the Zener voltage. Okay, so 9.1 volts. So it means if this thing regulates, this is my output voltage right here. This is my voltmeter on my output. And right now it's pretty dang close to 9.1 volts, right? Y'all understand that? So what I'm going to do is we'll start off first by adjusting this load. And what you got to understand, so over here I have 12 volts. Over here I have 9.1 volts. So what is that resistor right there dropping? Well, we need to, so what's it dropping? 12 volts on this side, 9.1 on that side. So what's it dropping? So it's dropping 2.9 volts. Okay, y'all understand that? So if this right over here does not change, if this 12 volts does not change, this resistor is going to drop 2.9 volts, which is going to make it's going to require about 29 milliamps to drop 2.9 volts. Y'all understand that? So if I don't change this voltage right here, then this current right here is not going to change. But watch what happens. So what I'm going to do is I'm going to start changing the load. So right now I've got 1K over there. Okay, so I'm going to come over here. Now I have 95. Now I have 95% of that. So what you notice, the current here did not change. Okay, while y'all here, guys, I'm going to record this. This class is supposed to meet 7 hours a week over 16 weeks. Why do we meet 7 hours a week? Or why do we meet 6 hours? Because what they've done to get you out of here early is they've moved the breaks to the end of the class. So legally, I'm supposed to get you in here and I'm supposed to have class for 3 solid hours with no breaks. But I know that's highly unlikely. I'll probably be able to do that. So what we do is we let y'all take 10-minute breaks. And if you don't think I can get up here and lecture for 3 hours straight without any problems, you got another thing coming. I can do that very easily. So if y'all if y'all don't come back in 10 minutes, that's what I'm going to do. If you got to go to the restroom, you get up and you go to the restroom while you're in class, and you'll just miss what we go over while you're gone. Y'all understand that? So we're losing 16 hours. I mean, we're losing an hour a week out of this class. That's 16 hours over 16 weeks. Y'all understand that? So don't take advantage of the breaks. Or I'll do the class the way I'm supposed to be doing it and teach and do 3 hours solid. And if you need to go to the restroom or take a break, what do you need to do? You just get up and go out and come back. It's kind of like our faculty meetings. So our faculty meetings usually go about 3 hours, and they have no breaks. They go solid. So if we need to go, we just do what? We go. So notice what happens, though. What I want you to notice is that the Zener is a dynamic device. It literally changes its opposition depending on to maintain that 9 volts. So if this guy's 9 volts and this current goes down, it means the Zener resistance had to go up. If this current goes up and this voltage don't change, it means the Zener resistance had to go down. So a Zener is a dynamic device. It's not like a resistor. It has a reverse bias resistance, but its resistance actually changes. So watch this. So if I make this load smaller, so if I go down to 90%, this current's going to go up, this current's going to go down, that current right there is not going to change. So here's 90%. So right now we got 9.6 milliamps of flow right here. We got 19.5 milliamps of flow right there. I did it. This current went up. This current did what? Went down. The voltage did not change. It's still about 9.1 volts. So what had to happen? Well, my load changed and my Zener's opposition changed. So its opposition actually went up because R is equal to V over I. So if V don't change and I goes down, that means the Zener resistance had to do what? Had to go up. Did I touch a dial? So I could sit here with a rheostat right here and I could simulate a Zener. So every time this guy needed more current, I would change the resistance of the rheostat, but this Zener's doing it automatically. Okay, so here we go. Okay, so now we're at, wrong button. Now we're at 85%. Notice the Zener voltage varies just a hair, but it's still 9.1 volts. This current went up. This current did what? Went down. This current did what? Stayed the same. Because this resistor is dropping the difference between my unregulated and my regulated. Okay, do it again. 75%. This went up. This did what? Went down. This guy here stayed basically the same. Okay, this is 70%. Can you see what's happening? So our output is staying at 9.1 volt, even though I'm changing the size of this resistor. I'm changing the load. Here's 55%. Still regulating, right? Still would be considered 9.1 volts. So now we got 9.076. And then sooner or later, it's going to go out of regulation. But look what's happening to the Zener. So I just went out of regulation. Why did I go out of regulation? Because I got below the knee current. Yeah, so now my Zener current kept dropping down. It kept dropping down. So see, so now we're regulating. Okay, we're right at the very end of not regulating. But as soon as I come over here and did this, notice what happened to my Zener current. So it dropped below the knee, and now we're out of regulation. So now if I come over here and I start changing my voltage, look what's happened to my output voltage over here. Now it's no longer 9.1 volts. My Zener current went to 0 because now we don't have enough current left over to operate it above the knee. Okay, so now we're back regulating, right? You understand that? So what I'm going to do is I'm going to vary my input voltage. We'll take it up to 14 volts. Now in real life, we would have to make sure this didn't exceed the Zener. Okay, I'm going to turn it back on. And notice it's still 9.1 volts. This current right here, since I'm not changing my load. So my load current is not changing. But my Zener current went up. Because now this resistor, instead of dropping 2.9 volts, now it's having to drop, what, almost 4 volts. So the current through this went up. The current through the load didn't go up because it's looking at 9.1 volts. So the current in the Zener resistance actually went down. So what happens, now well, let's drop the voltage down. What do you want to go down to? Can't go down too far. Let's go down, it was 12. Let's go to 11 volts. Voltage over here stayed at 9.1. This current right here stayed the same. Zener current went down. So if my input voltage, if my load if my load doesn't change, if my input voltage goes up, my Zener current automatically goes up. If my input voltage goes down, my Zener current automatically goes down. So my Zener current varies in the same direction as the voltage. My load current, if my load current goes up, my Zener current goes down. If my load current goes down, my Zener current goes up. So Zener current varies opposite of the load current. Now, of course, it's doing this all the time, right? You understand, but we can't. So what we do is we vary the input voltage over a range, and then we vary the load over a range. So if I drop it down to 9 volts, what should happen? Well, it's a 9.1 volt Zener. So if I drop it down to 9 volts, it should go out of regulation, right? So notice my Zener current went to what? 0, and now my output voltage is at 8.2 volts instead of 9.1. So as long as I operate it above the knee, it works. It regulates real good, right? I mean, it varied a little bit. It's got to, but it did a really, really good job. So that's what's so neat. This guy is actually doing what? It's varying its resistance to maintain a constant output, and it's doing that dynamically. So you're not turning a pot. So I could come over here and change this with a rheostat and raise the voltage and lower this. I could lower this too, right? You understand? If I did it at the same rate, but now I'm going to have to turn a pot. This guy here dynamically changes its resistance. But if I choose a resistor that's too big, now if I choose a resistor that's too big, we'll go back up to 12 volts. And we're still out of regulation. See, because this guy right here, we're trying to get at 5 milliamps. So it's so the current this guy's using and this guy's using, that's 12 milliamps, and the 1K resistor drops all the volts. Right? You understand? So if I use a resistor too big, it's not going to regulate. If I use a resistor that's too small, what will it do? It'll burn my Zener up. So that's 20 ohms. I'm pulling 130 milliamps here. So that would be 130 milliamps times 9.1 volts. What would be my power in my Zener? 9.1 times 0.134. That's 1.2 watts. It's only a 1 watt Zener. We just burned it up. So if I choose a resistor that's too small, we'll burn our resistor up, right? You understand? And this is if I do this. If I come over here now and start changing my load, or my input voltage goes up to 14 volts, but if I come over here and start making this load smaller, my Zener current just does what? Oops, wrong way. But now if my unregulated goes up to 14 volts, then we're really going to burn it up. So what we're going to do, choosing this resistor right here is really critical, but it's not hard. We're going to use Ohm's law. All we got to do is figure out what V and what I. So why do we want this resistor right here to drop? So what we want to do is we want to always move this toward the knee. So let's put this at 12 volts. Okay, so we have Zener current, right? You understand? Now, if I raise this voltage up, Zener current is going to go up. So we're moving away from the knee. If I bring this voltage down, then the Zener current is going to go down, so we're moving toward the knee, right? You understand? Your target current is operated above the knee if you want to operate it over the widest range. And it still regulates really well. I mean, this is, let's see if we can get close to the knee. What would that be? Let's put 10 volts up there. But watch what happened to the knee. So it went what? It went down, right? You understand that? So we're going to operate it, we're going to make sure we operate it above the knee. But my lowest current occurs at my smallest voltage.
That's what I'm saying. If you were sitting here figuring this circuit out, you want to start it, you want to keep it, turn it close to the end possible.
No, we want to keep it between the knee and IZ max. What you got to understand is normally these power supplies are going to vary their loads. Okay. So we're going to design it to operate always, worst case scenario, to operate above the knee. And then we're going to choose then we're going to make sure we never operate it above IZ max. So we want it to be above the knee or more than the knee and less than IZ max. And in that way we can vary it over a range, right? So right now when you go over there and get your power supplies and you put them out there and you turn it on, those regulators are unloaded. So that means my load current is 0. And then we start loading them, right? You understand? Well, if my load current starts going up, what happens to the Zener current? Well, the Zener current goes down. So what we want to do is we want to choose a resistor that drops the minimum voltage at the maximum current. So that way, if the load current goes down, you move away from the Z. If your input voltage goes up, you move away from IZK. Does that make sense? So y'all get out y'all's formula sheet and look and see how do we calculate RS. So let's explain that. All right, it should be self-explanatory. The first thing I'm going to do, guys, is I'm going to figure out what my unregulated voltage is going to give. So what do y'all want to do? What Zener do y'all want to do? Y'all pick out one.
One in 4, 7, 4, 6.
Okay, so 1N 47, 46. Okay, what's the Zener voltage? Okay, Zener voltage is 18. And what's IZK?
No. Yeah.
250 microamps, right? 0.25 milliamps. Okay, they'll follow me so far. And it's an 18 volt Zener. I don't know why I put M up there. It's an 18 volt Zener. So it means we're going to have to have an unregulated voltage that's more than that. So let's say we're going to choose a power supply that goes between 20 volts and 24 volts. And we know we can do that. We know we can find a transformer. We know we can calculate the size of the capacitor to give us the ripple voltage that we want. Y'all understand that? Okay. Okay, so now we're going to have a load. What do we want to do with our load? What is our load current going to vary between? Now let's vary it between 0 so we can unload it up to some current. What do y'all want to go up to? We're going to have to be in the milliamps. What do y'all want? Can't get much current out of this guy. Huh? Give me one. 10 milliamps? That's good. So this is going to be a small power supply. Okay. So what do I want to do? Well, first of all, I'm going to choose that resistor right there. And it's critical. So first thing I'm going to do is I'm going to calculate the maximum and the minimum voltage. That resistor's got to drop. So VR max is going to be equal to 24 volts minus 18 volts. Y'all understand that? So what's my maximum voltage that's going to drop? Very easy math, guys. 6 volts. Then I'm going to calculate my minimum voltage, VR minimum. So I'm going to take 20 volts minus 18. So the minimum that resistor will ever have to drop is 2 volts. Not so bad so far, right? You understand? Okay. So what are we going to do now? Well, I know if my voltage goes down, Zener current goes down. So RS, we're going to start off. This is RS minimum, by the way. We're going to look at this. We're never going to use this resistor. I'm going to use 2 volts, right? You understand? All right. Then my maximum current, minimum voltage, maximum current, 10 milliamps, plus IZK, 250 micrograms. So there's R is equal to V over I. This is Ohm's law. We just figured out what V to use, which V to use that would drive it toward the knee. So if this voltage goes up, it's going to move away from IZK, right? You understand? So what we're doing is we're saying, okay, what's the worst case scenario? So what do we got for RS? What's that? K ohms? Pretty good size resistor. Very low current though. Are we okay? Now what are we going to do with that? Well, there's no such thing as a 7.969K resistor. So we're either going to round this up to the next standard value or we're going to round it down to the next standard value. What are we going to do? We're going to round it up or round it down. If I round it up, we're going to be moving toward a 7.69 resistor would put it at the knee. We don't want it to be at the knee. We want it to conduct more than the knee, right? You understand? Yes or no? Okay. So we'd round it down. So what's the next standard resistor, guys? Don't know. We'll look it up. We got the standard resistor chart somewhere on Blackboard. Probably in handouts. Transform calculations, formula sheet, standard resistors. So these are standard resistors. So we have and they move in these, so here's a 7, so we come up here, what did we calculate?
Okay.
Okay, so that means we would try a 6.8. $6.8. Okay. Let's say we're going to use a 5%. So I'm going to multiply this by 1.05. And what does that come up and give me? What's that? Okay, so this looks good. This is, I'm sorry, this is maximum right here. This is not minimum, this is maximum. So I went over here and I multiplied it by the tolerance. It came up to be less than my maximum, so we would use a 6.8K. If it came up to be more than my maximum, I would go down one more resistor. Y'all understand that? So 6.8K. And that's because this is a little old tiny power supply. Okay, so what do I need to calculate now? So we chose our resistor. Now this guy here's gone. We're not going to use that anymore in our calculations. Now we're going to figure out resistors are, we've taken care of the tolerance, right? You understand that. So if we use a 5% tolerance, it could be 5% high and we're okay, and 5% low makes no difference. Okay. So what else do we need to know about that resistor? We need to know the wattage rating. So I'm going to say, okay, PRS is going to be equal to the maximum voltage it would ever drop, 6 squared over its size. V squared over R. 5 point what? 5.3 milliwatts. So we could use an 8 kilowatt resistor there. We could actually use one smaller, but that's the smallest one they make without going to surface mount. Odds are we'd use a quarter watt. Why do you think we'd use a quarter watt? Because they're cheaper than 8 kilowatts. Not unless I was limited to space. Okay, now guys, we're going to figure out if we're going to burn up our Zener. So how am I going to do that? So PZ, we're going to use IZ max. Well, let's do this a little different. So what laws have we used so far? Ohm's law. Now, and we've used Watt's law. So we used Ohm's law and Watt's law. Where did y'all learn those at? DC. But now we're applying it to something that's actually dynamic. So this is going to be equal to VZ times some current. So what's the maximum current we could have in our circuit? The maximum current we could have in our circuit is when that dang resistor is dropping 6 volts. That's the maximum current. It's a series resistor. All the current goes through there. Okay, you understand that? So my Zener current is going to be equal to that. So I'm going to take 6 volts. I'm going to divide it by 6.8 K. And then I'm going to subtract from that the minimum current that would flow through the load, which would be what? 0. And then this will be our power in our Zener. Yeah, I think our 1 watt Zener would be fine. What you got? I put amps out there, so I did something. I just broke a cardinal rule. If you did that on a test, I'd count it wrong, right? Yeah, so we wouldn't even have to use the 1 watt Zener. We could. I'm not doing the calculations. You're looking strange to it. I would probably work on this backwards. So first of all, we figured out the maximum current flow through this resistor right here. This is a series resistor. Whatever current flows through that flows through the whole circuit. Then I got to figure out, okay, how much of that current is going through the Zener and how much of that is going through the load. Well, right here we said we could have what? Because I hit that dot right there, and it means those two currents are shared. So if we have 0 current flow that way, that means all that current has got to go through the what? Through the Zener. So that's what we do right there. So I came over here and I keep going by. I get too fast. I need to go a lot slower. So what I did is I took what? I took 6 and divided it by the size of my resistor, 6.8 times 10 to the third. Right? And then what I do? Then I multiply that times the Zener voltage. What's our Zener voltage? 18 volts. And that gave me that. That's what I came up with. Did I mess up? Yeah, you just can't take that answer. So we would have burned our Zener up. Yeah, power is equal to V times I. We're using this to calculate what? I. And then our Zener voltage would be the voltage drop across the Zener. Okay, then if I do what? I take 6, divide it by 6.8 times 10 to the third negative, right? And then I multiply that times what? 18. That's what I'm coming up with. What am I doing wrong? 6 divided by 6.8. Oh, I know what I'm doing. Duh. Y'all didn't catch me on it. Times 10 to the third. I'm not gonna tell you what I was doing. Then we come up here and multiply it times 18. So 15.8 milliwatts. So this will be fine. And
6 over 2.8.
minus 0. What you're doing is you're seeing when the current through the zener would be maximum. So what we're going to do is we're going to look at this load right here. So we're designing this power supply to go from what? From 0 to 10 milliamps. So what you're doing is if my load is pulling the minimum current, then my zener current is the maximum. But we always got to subtract that, right? You understand that? So some of y'all are going to do on the worksheet that I'm going to give y'all. Some of you do on the worksheet. The power supply is never unloaded. So it's just like your car, your batteries, your alternator is never unloaded. But the load is going to do what? It's going to vary. Well, to figure out how much current flows through the regulator, you'd have to figure out, okay, is used by the regulator to regulate is how much your load needs, and then you'd subtract that to get how much current is used to run your regulator. Regulators, we don't ever get anything for free, right? You understand that? So if I get 100 watts out of an amplifier, it's going to take more than 100 watts to run it, because you got to run the amplifier. Not only you got to run the power going to your speakers, but you got to run the amplifier, right? You understand that? So there's nothing out there that's 100% efficient. We always get lost. So if you got a big power amp and you looked at what current you put into it and what watts you get out, you'd see that the watts in is always going to be greater than the watts out.
6 came from.
Oh, dang it. The 6 came from what we did, and I just erased every bit of that. What we did is we looked at the maximum voltage this resistor right here would ever drop. This is a series resistor. And what's in the series resistor, all the current in the circuit flows through that resistor. Now I know I is equal to V over R, but I have no idea what the resistance of the zener is. Why do I know the resistance of the zener? Because it's dynamic, it's constantly what? Changing. But by George, I know the resistance of that RS right there. I know it. How do I know it? Well, I calculate it, right? So if I wanted to calculate that resistance in that circuit, then I take the maximum voltage it was ever dropped. So one of the things we calculated at was VR max, right? VRS max. And what was that? That was 6 volts. And so I know the maximum current that would ever flow through that resistor. So IRS max would always be what? Would be the maximum it would be 6 divided by 6.8K. Understand that, Mitchell? Okay. And what did that come up to be? What did it come up to be? What's that? 882? That's going to be close to 1. Are we okay? Now you know where it came from? Then what we did is we know that the current flow through this guy here has 2 paths. I'm drawing positive current flow, by the way. It's got 2 paths, right? You understand that? So how much flows through the zener? Well, what flows through the zener would be IR max minus I the load minimum, which now is 0, right? You understand that? But it don't have to be 0. So whatever that comes out to be, that's when the worst case, that would be the most current flow through the zener. And then we multiply that times what? Times VZ, and that gives me the power of my zener. And as long as it goes below the zener that we're using, we're okay. If it goes above it, then we got to find another zener. And there's all kind of zeners out there, right? You understand? So the 4700 series of zeners are 1 watt zeners. But there's 2 watt zeners. There's 5 watt zeners. I think there's up, I don't remember how high they go up to, but they can go up pretty high. They'll come in metal cases. They'll be heat sink. So we can get some pretty high wattage zeners.
Do they follow the
Huh?
Do they follow the 125 standard?
Resistors don't even follow the 125 standard. So guys, let me go ahead and give you all a worksheet and then we'll split. This will be due in class. So after we go through the worksheet, we'll be in lab Monday. The test is Wednesday, right? Wednesday test? Wednesday? Yes? Huh? Yeah, because digital is Tuesday, so Wednesday. So what we'll do Monday is we'll go over the worksheet to start off with. I'll give you all the answers, and if y'all got any of them we want to work, we'll do that. And then we'll be in lab the rest of the day on Wednesday. Monday. Then Wednesday we'll start off in lab before the test, and then we'll have the test at the end of class. We was going to be in lab today, but Barry brought it to my attention. So that's why we decided. We was either going to have to lecture today or lecture Monday. And he thought it would be better if we lectured today instead of Monday. And the test is on Wednesday. So y'all can thank Barry for that.